Hi, welcome to AB Video 6.2b Part 2, the end of growth and decay, simpler version. So here's what we're going to do. We're going to circumvent that. All right, so here's Newton's law of cooling on the worksheet, which is not that, which is this. No, not that. Got to be one of them, doesn't it? Okay, it's not that one. It's not that one. I swear I opened up this worksheet. I could have sworn I opened up this worksheet. What's this? No, no. Up more. There it is. Oh, for goodness sake. There. Okay. All right. Yeah, but I don't know where everything else is now. Okay, I think it was number 24. So let's look at 24. A pot of water was initially boiling at 100 degrees, was cooling in air at a temperature of 0 degrees. After 20 minutes, the temperature of the water was 90 degrees. After how many minutes will the temperature of the water be 80 degrees? And what was the temperature 1 hour after use? Okay, so the room temperature is 0. This is our formula, dy dt equals k times y minus t. They'll give you this equation, differential equation, or they'll write it out in words and you can translate. Okay, so in this particular case, it's easy because the room temperature is 0. It does become dy dt equals ky, and we change it to y equals y0 times e to the kt. And you started off with this at 100-degree temperature, and then they told you 20 minutes later the temperature was 90 degrees. So you'll be able to solve for e to the 20k. Then what I do is I take this equation, break it up into this, replace e to the 20k by 9/10. So I have this equation, but I replace e to the kt by e to the 20k to the t over 20, and e to the 20k is 9/10. Okay? Once you have your equation, notice in y and t, the next question is how long will it take to cool down to 80 degrees? So you write the temperature of 80 degrees, solve for t, which is your time in minutes. And the last question is saying what will the temperature be after an hour? So you're going to replace t by 60 minutes because everything's done in minutes. And again, you'll use your calculator. Actually, this one you can do by hand. You get 72.9 degrees. Okay, so here it is again, that same formula, but let's take a case where the room temperature is not 0. Okay, so let's pretend the room temperature is 60. Now, you could try and solve that differential equation. That would not be fun. So we're going to do a substitution. What we're going to do is we're going to say, you know what, let's let u equal y minus 60. If we do that, then d dt of each side becomes du dt equals dy dt minus 0. So it turns out that du dt is the same thing as dy dt. So if I take this equation, I can replace dy dt by du dt. I can replace y minus 60 by u, and now I have this, and this does become u equals u0 times e to the kt. So you started out in this case, I don't know which problem this is. Oh, here we go. So an object cools from 100 degrees to 90 degrees in 30 minutes. Oh, that would be over here. Okay. So, oh, exactly. Now, what this is for the original value of y. So y goes from 100 degrees to 90 degrees in 30 minutes. So which means the y0 is 100, and then when t equals 30, your y will equal 90. So our y0 is 100, but of course y is equal to, if you solve that, y is equal, sorry, u is equal to y minus 60. So if I replace y by 100, I get u is equal to 100 minus 60, which is 40. So my initial u, my u0 is 40. Then y is equal to 90 degrees. Well, if y is 90, u is 30. So that's the initial u, and that's the final u. So I can replace u0 by 40. I can replace u by 30, and they say it takes 30 minutes for that to happen, so I replace t by 30. If you had a calculator, you could solve for k. I don't, so I'm writing this as e to the 30k equals 3/4, and then I'm rewriting this e to the kt purposely into e to the 30k to the t over 30, so I can replace the e to the 30k by 3/4. Now, you will need to go back, replace u by y minus 60, replace u0 by 40, and now isolate the y, and there is your beautiful equation in y and t. Okay, number 28. Number 28, a new worker on an assembly line could do a particular task in such a way that if Y units are completed per day after T days on the assembly line, then this is your differential equation. Slightly different than what we had before. Before we had Y minus the constant room temperature. This is a constant minus Y. Tells you K is positive constant. Tells you Y is less than 0 for all T greater than or equal to 0. Sorry, Y is less than 90, which means this quantity will be positive. On the day the worker starts, 60 units are completed, and on the 5th day, the worker completes 75 units, etc., etc., etc. Okay, so so that's given to us. It's also given to us that y is less than 90. So again, this is an ugly one, so I'm going to let u equal 90 minus y, which makes du equal negative dy dt, which makes dy dt the same thing as negative du dt. So replace dy dt by negative du dt, replace 90 minus y by u, send that negative to the other side, and now I have u equals u0 times e to the negative kt. Now, we started out with 60 units. On the 5th day, there were 75. So when t equals 0, y is 60, which means y0 is 60. But of course, if y0 is 60, then u equals 90 minus 60, which is u0 is 30. Then it says after 5 days, there's 75 units. So what I'm going to do is put that in terms of u. Well, if y is 75, then u is 90 minus 75, which is 15. So I replace my u0 by 30, my u by 15, and it takes 5 days for that to happen, and blah, blah, blah. Same thing. You could solve for k if you had a calculator. If not, blah, blah, blah. Put it back in terms of y. So what's y after 9 days? Replace t by 9. And what happens? What's y after 30 days? Replace t by 30. Same old, end of video.